Okay, I want to finish up our discussion of logic today, and obviously, like, there is we could talk about a lot more things in logic. There's a course here at COS that you can take all about logic, and it would require the entire semester just to kind of scratch the surface on it. And so we haven't even scratched the surface. There is a ton more that we could talk about with logic, but for the purposes of this class, I mainly just wanted to give you some idea of what logic is, because math is largely just an exercise in logic. Okay, so to round out our discussion of logic, I wanted to talk about syllogisms and using Euler diagrams to verify the validity of syllogisms. So a syllogism is an argument that may contain quantifiers. So all of the arguments that we saw in the previous section, none of them used quantifiers, right? So you may recall from our discussion a few lectures back that quantifiers are words such as all, some, and none. And like the arguments that we considered in the previous lecture, we consider a syllogism to be valid if whenever its premises are all true, its conclusion must also be true. And by the way, I should mention something now that maybe I should have mentioned before, but just for your information, the study of arguments that only use statements and connectives, like the ones that we studied in the previous lecture, that is called propositional logic, whereas the study of arguments that involve quantifiers, like the syllogisms we're discussing now, that's called predicate logic. So predicate logic is a little bit more complicated than propositional logic. And we'll see why in this section, but here's an example of a syllogism. This is a very famous syllogism, right? So the syllogism goes, all people are mortal, Socrates is a person, therefore Socrates is mortal, right? So that's a syllogism, and note that it's valid, right? If we assume that these two statements are true, that all people are mortal and that Socrates is a person, then it follows that Socrates must be mortal, right? So that's valid. Also note that we could replace this first statement, all people are mortal, with a logically equivalent statement. If object A is a person, then object A is mortal, right? So person implies mortal. So we could replace the first statement here with the quantifier and just replace it with a statement that doesn't use a quantifier. If we were to do that, notice that the other two statements don't use any quantifiers, and so that would convert this syllogism into an argument of propositional logic, right? And so then we can make a truth table to evaluate the validity of that argument. However, it's not always possible to do that, right? We can't always turn predicate logic into propositional logic, and we'll see some examples a little bit later on where it wouldn't really be possible to turn the statement into a statement of propositional logic. And that's a problem for us because truth tables also don't really work very well with predicate logic. So whenever we have these quantifiers, all or some or none or things like that, then truth tables aren't really going to help us. Truth tables don't really work. So consequently, we're going to use a different strategy to evaluate the validity of syllogisms. And the strategy we're going to use is we're going to look at Euler diagrams. And I know it's kind of weird. The name is spelled E-U-L-E-R, but it's pronounced Euler. It's pronounced Euler. Okay, so we're gonna evaluate the validity of syllogisms using Euler diagrams. So without further ado, let me just give you an example of how we would do this. Now we actually saw some Euler diagrams earlier on before we even started talking about logic. So you should have some idea of what an Euler diagram is, but if not, you'll get the hang of it as we go through these examples. So example 1 says, use an Euler diagram to determine whether the syllogism is valid. Okay, and the syllogism that we're given says, all poets are good spellers. Dante is not a good speller. Therefore, Dante is not a poet. Okay, so here's how we can create an Euler diagram. So So I'm going to draw a circle, and this is going to represent, it says all poets are good spellers. So all of the poets, so I'm going to draw a circle representing good spellers, and I'm going to draw a circle representing poets. But since all poets are good spellers, the all poets circle should be inside of the good spellers circle. So I'm going to draw a circle. This is going to be good spellers. And inside that circle, I'm going to have another circle for poets, right? So this represents that first statement. All poets are good spellers, right? So poets are a subset of good spellers, you might say, right? The second statement says that Dante is not a good speller, right? Dante's not a good speller. So that means that Dante cannot be inside of this bigger circle, which means he can't be inside the smaller circle either. He's got to be outside of there somewhere. So maybe this represents Dante, right? He's just a little point, right? Because he's just a single individual. So Dante is not a good speller, right? So that represents the second statement. And then the conclusion is that Dante is not a poet. Well, yes, that's valid, right? If all poets are good spellers, then all poets have to live inside of the good speller bubble. If Dante's not a good speller, then he lives outside of the good speller bubble, and therefore he can't be a poet, right? So Dante's not a poet. That's valid, right? So we say the syllogism is valid. Now, a quick word about this, and we saw this in the previous lecture as well, right? Is that you may believe it's possible for a person to be a poet without being a good speller, right? But your feeling about this premise is not relevant to the validity of the argument. Relevant. Shouldn't have any. But it's not relevant to the validity of the argument, right? So in other words, the validity of the argument has nothing to do with whether or not the premises are true. It only has to do with if we assume the premises are true, does the conclusion follow with necessity from the premises? And in this case, it does. So the problem with this argument, because I would agree that this argument is flawed, but it's not flawed because it's not a valid argument. It's flawed because one or both of these premises are not true. Okay. But if we assume the premises are true, then the conclusion must follow, and so this is a valid argument. So it may interest you to know, because I can sense that this probably bothers some of you. And so it may interest you to know that a valid argument with true premises is called a sound argument, while a valid argument with at least one false premise is unsound. So in this case, this argument would be valid but unsound, because it's not necessarily true that all poets are good spellers, right? You could be a bad speller and still be a poet. So the problem is not the format of this argument. This argument has a valid format. It's just that the premises, the first premise in particular, is not a true statement, and so that's why you're ending up with with this unsound argument. So it is a valid argument, but it's unsound. Anyway, in this section, we're not really going to look at soundness. What we're going to look at is validity. So all we're interested in is the validity of the argument. So we don't really care if the premises are actually true or not. What we care about is if we assume that they're true, does the conclusion follow with necessity? And in this case, it does. So this syllogism is valid. Okay, moving on. Let's look at another example. So example 2 says, use an Euler diagram to determine whether the syllogism is valid. So same as the previous example. Okay. This one says, all tigers are meat eaters. Simba is a meat eater. Therefore, Simba is a tiger. Okay. So let's see if we can draw an Euler diagram to determine whether this syllogism is valid. So it says all tigers are meat eaters. So again, we're going to draw two circles, two bubbles, one of them for tigers and one of them for meat eaters. And then Since it says that all tigers are meat eaters, that means that the tiger bubble should fit inside of the meat eater bubble. So, so I'm going to do this. So this box is just going to represent, you don't really need the box, I guess. I don't know why I drew the box. But the box kind of represents like all of the possibilities, I guess. But anyway, we're going to draw a bubble representing meat eaters. And then we're going to draw another bubble inside of that bubble representing tigers, because all tigers are meat eaters. So all tigers should be inside of this larger meat eaters bubble. Okay, so that's the first statement. All tigers are meat eaters. Now the second statement says Simba is a meat eater. Okay. All right, so Simba's a meat eater. So Simba belongs somewhere inside of this meat eater circle. If we put Simba right here, right, then the conclusion Simba is a tiger, that's true the way that we've drawn this diagram. But notice that there's another possibility. We didn't have to draw it that way. We could have drawn Simba we could have drawn it like this. Okay, so you've got meat eaters, you've got tigers, and then all the second statement says, it doesn't say Simba's a tiger, it just says Simba's a meat eater. So maybe Simba's actually out here, right? And in that case, you can see that the conclusion Simba is a tiger is false, because he's not inside of that little circle. So just like with the truth tables, so when we looked at the truth tables to verify arguments in the previous section, what we said was that if there's even one example where all of the premises are true but the conclusion is false, then the statement is not valid. It's the same way when you're drawing Euler diagrams. If there's only one way that you can draw the Euler diagram to make the conclusion not true, that means that the syllogism is not valid. So if we draw it this way, it seems like it could be true, but if we draw it this way, it's very clear that the conclusion does not necessarily have to follow from the premises, and so this is not a valid syllogism, right? So the syllogism is not valid because of that, right? Okay, let's look at a couple more. It says, assume that a syllogism begins with the following two premises. So premise 1, no MacBooks get viruses, and premise 2, my laptop does not get viruses. Part A asks us, can we conclude that my computer is a MacBook? Okay. So let's see if we can use an Euler diagram for this. So it says, no MacBooks get viruses. So we're going to have two circles, a circle for MacBooks and a circle for things that get viruses, right? I'll just call it maybe get viruses, right? So MacBooks, so we need a circle for MacBooks, and then we need a circle for get viruses. When this first statement says no MacBooks get viruses, then that means there can be no overlap between those two circles. Okay, so there will be a circle for MacBooks and a circle for get viruses, right? Things that get viruses. No MacBooks get viruses. So that's that first statement. Now the second statement says my laptop does not get viruses. Okay, my laptop does not get viruses. So if your laptop does not get viruses, then that means it doesn't belong inside of this circle of things that get viruses, right? It's not part of that. So that means that your MacBook could be, or not your MacBook, that means that your computer could be here, So my computer, okay, or my laptop, whatever. So that's one way that you could draw it. But you could also draw it this way, right? You could say, well, here's the circle for MacBooks. Here's the circle for things that get viruses. And here's my computer, right? Maybe it's not in either of these circles. It's not something that gets a virus, but it's also not a MacBook. So the question, can we conclude that my computer is a MacBook? No, because this is also a possibility, right? Your computer could be something other than a MacBook that also doesn't get viruses, right? So the answer is no. No, we cannot conclude that my computer is a MacBook because this is a possibility. Possibility. Man, I have a hard time spelling sometimes. But this is a possibility. So, so your MacBook or your computer doesn't necessarily have to be a MacBook. Okay. Well, part B. Can we conclude that my computer is not a MacBook? Well, we've already done all the work, and the answer is once again no, because this is a possibility. And this would be that scenario, right? So can we conclude that my computer is not a MacBook? No, maybe it is. So maybe it is, but maybe it's not. So we can't conclude that your computer is a MacBook, but we also can't conclude that your computer is not a MacBook. Okay. So we've seen some syllogisms with the all quantifier, and we've seen some syllogisms with the no quantifier. Let's talk about syllogisms with the some quantifier. These are the harder ones because, you know, as we saw in the previous example, we can often represent a syllogism with more than one Euler diagram, but that's especially a problem for the some quantifier because there are several different ways to represent some in Euler diagrams. So for example, the statement some A's are B's can be represented by any of these Euler diagrams, right? It could be that A's and B's just share a little bit of overlap, or it could be that A's are completely contained inside of B's, right? In other words, this says that all A's are B's. Well, if you say some A's are B, that doesn't exclude the possibility that all A's are B's, right? So when you say some A's are B's, it could be that actually all A's are B's. That's a possibility. But another possibility is that all B's are A's, right? If some A's are B's, this is another possibility, right? Some of the A's inside of this bubble are also B's. So any of these three could be what we are describing when we say some A's are B's. And so that makes working with the quantifier some a little bit tricky sometimes. Again, what you have to do when you're trying to decide if a syllogism is valid is you have to look at all of the possibilities, and if even one of them has the scenario that the conclusion doesn't follow with necessity from the premises, then that means the syllogism is not valid. So let's look at a couple examples. This first one says, is the syllogism valid? All cars manufactured after 2007 have driver-side airbags. Some cars with driver-side airbags have passenger-side airbags. Therefore, some cars with passenger-side airbags were manufactured after 2007. Okay, so let's think about this. All cars manufactured after 2007 have driver-side airbags. So we need two circles, one for driver-side airbags and then one for cars manufactured after 2007. And since all cars manufactured after 2007 had driver-side airbags, that bubble representing cars manufactured after 2007, that's going to be Well, there are a couple different ways to think about it. Well, that bubble has to be... Actually, no. That bubble has to be inside of the bubble for driver's side airbags, right? Okay, so here's what we're going to have. So driver's side airbags, I'm just going to call that DSA, driver's side airbags. And then cars manufactured after 2007. So say after 2007, right? So that's that first statement. All cars manufactured after 2007 have driver's side airbags. There may be some cars with driver's side airbags that were manufactured before 2007, right? But all cars manufactured after 2007 had driver's side airbags. So there's the first statement. But the second statement now says some cars with driver's side airbags have passenger side airbags. Okay, so we need a third bubble, one for passenger side airbags. And here's where things get tricky. So it says some cars with driver's side airbags have passenger side airbags. How do we draw that? Well, we could draw it like this. Say passenger side airbags, right? So some cars with driver's side airbags have passenger side airbags, right? So that would be this place where they overlap, right? These are the cars that have both driver's side airbags and passenger side airbags. So there's one way that we could draw it. How else could we draw it? Maybe it looks more like this. Maybe you have driver's side airbags after 2007, and then you have this scenario, right? This would still satisfy both conditions, right? It would say all cars after 2007 have driver's side airbags, and then some cars with driver's side airbags have passenger side airbags, right? This would be another way to draw it for that matter. So maybe I'll put boxes around each of the different possibilities. Another way you could draw it would be to have those little circles overlap. So driver's side airbags, and then after 2007, and then passenger side airbags, right? So that's another distinct possibility. Oh man, there are a whole bunch of different ways that you could draw this. Because maybe it's more like this. Okay, maybe it's more like driver side airbags, passenger side airbags, and then maybe cars manufactured after 2007. Looks like that, right? Because after 2007 is still contained entirely inside of the driver side airbags, but you also have some driver side airbags with passenger side airbags, right? So all of these are possibilities. There are more ways that we could draw this. I haven't even exhausted all of the possibilities, right? So these are just 4 possibilities, but there are more. The point is, do any of these pictures contradict the conclusion, right? The conclusion is that some cars with passenger side airbags were manufactured after 2007. And the answer is yes, we do have some contradictions, right? Like this very first Euler diagram that we drew contradicts that conclusion, right? Because here you have passenger side airbags, and none of them were manufactured after 2007, right? Same thing here. You have all of your passenger side airbags here, but none of them were manufactured after 2007. Here, this would confirm the conclusion, and so would this one, okay? But as long as you have at least one Euler diagram that contradicts the conclusion, you've got an invalid argument. And here, we have 2. I'm sure there are more ways to draw this, and there might be more ways to draw it so that you get an invalid conclusion, or you get a contradiction of the conclusion. But But all you need is at least one, and we've got two. So this argument is invalid. Okay? It seems like a reasonable conclusion, but we just don't know it for sure. It doesn't have to follow with necessity from the premises. So it's not valid. Okay? It's invalid. Okay, one more. This one says, is the syllogism valid? And it goes, all firefighters are brave. Some firefighters like pineapple on their pizza. Therefore, some people who like pineapple on their pizza are brave. Okay. So we need two circles for this first statement. We need a circle for firefighters, and we need a circle for brave people. And the firefighters, all of them are brave. So the firefighters are going to live inside of the brave circle. Okay? So we've got brave people, and all firefighters are brave. Maybe it's true, maybe it's not. But anyway, that's what the statement says. Next statement says, some firefighters like pineapple on their pizza. And now here's where this gets crazy, right? Because there's so many different ways to draw that. Some firefighters like pineapple on their pizza. Maybe it's so one way that we could draw it is we could have a circle like this for people who like pineapple on pizza, right? So that's one way we could draw it. Another way we could draw it is you've got brave people, you've got firefighters, and then you've got people who like pineapple on pizza, right? That's another way that you could draw it. How else could we draw it? You could draw it like this. Brave, firefighters, and then pineapple on pizza, right? You could draw it like that. Okay? Now there are a bunch more ways that you can draw it, but what you realize after you do this, after you draw several of these diagrams, you realize that there has to be at least some overlap between the firefighters and the people who like pineapple on their pizza, because some firefighters like pineapple on their pizza. And then you also realize that firefighters have to be inside of the brave circle because all firefighters are brave. So the only way you can get an overlap between firefighters and people who like pineapple on their pizza is for at least part of the circle of people who like pineapple on their pizza to be inside of the brave circle, right? Like no matter how you draw it, this circle, at least part of this circle has to be inside of the brave circle. Okay? And so then the conclusion, some people who like pineapple on their pizza are brave, that has to follow. Right? So this argument is valid. Okay? And it should make sense, right? Just reading through the argument, all firefighters are brave, and some firefighters like pineapple on their pizza. So we know that there's at least one firefighter who likes pineapple on their pizza, and because that person is a firefighter, he or she is brave. And so therefore, there is at least one person who likes pineapple on their pizza who is brave, right? Has to be the case. So that's a valid argument for sure. And that's it. So kind of a relatively short section. That's all I wanted to say, just to, like I said, to kind of round out our discussion of logic. So that'll do it for that.